G'day everyone. In this video I'm going to be covering question 4 from the self-study questions sheet number 4. In this case we're looking at a case that does involve a discrete probability distribution, although that hasn't come out of it yet. However, this is an applied question, so instead of being given the discrete probability distribution and answering questions, you first have to extract that out of the information. So let's have a read through the question. Says, before I begin, I've chosen this question deliberately as it has a strong similarity to a question that will be of great importance to all of the people in the class over the next couple of weeks. Okay, so reading the question. I may have deleted a word here. A couple would love to have a girl and decided to have children until they have a girl. But they also agreed to have no more than 3 children. You want to construct a probability model to find out the expected number of children in this family. You decide that the random variable of this model should be a number of children x in this family. Assume boys and girls are equally likely. This will become important later. So in this case, we're going to introduce a variable x representing the number of children in the family. So as it says, it's a process whereby we do something, and then depending upon the outcomes, we either continue or we stop. So in this case, we stop once we hit a girl. We have 2 conditions that we stop. We either stop when we have a girl, or we stop when we get to 3 boys, i.e. we're going to have no more than 3 children. So if we consider the number of the different values that x can take, it can be 1, 2, or 3. So we can't have a situation of x equaling 0 because we need to have at least 1 girl. So we can't have 0 children in any of these families. In terms of the different values, 1, 2, and 3, 1 here represents 1 child in the family, so that would be obviously when we have a girl on the first go. 2 children would represent a situation in which we had a boy on the first go. Obviously we want a girl, we keep going. On our second try, we get a girl. The third option has 2 possible situations. It can be either we got a girl on the third and had a boy for the first and the second, or we have 3 boys and we've said that's it, we're not going to continue doing it. So in order to find the probabilities associated with this, we just need to consider the different situations in which the number of children, 1, 2, or 3, can occur. So for probability x is equal to 1, that's the same as the probability the number of children is equal to, number of children is equal to 1, And so the only time we can ever have that is when we have a girl on the first go. So I'm going to force a imposition within here of independence between different births. So what I mean by that is one birth doesn't affect the other birth. So if I have a boy first, it's not going to influence the outcome of having a boy or a girl next. So therefore, the probability of x equaling 1, which is the probability of number of children equals 1, is the probability of having a girl first, or the probability of just having a girl in any of the pregnancies. So here, this is where we use the information that we're going to assume the boys and girls are equally likely. So we have an equal probability of getting a boy as we do for a girl. So therefore, the probability of getting a girl first, which marries up with the probability of x equaling 1, is equal to 0.5. So let's put that into our table. Okay, so for x is equal to 2. So again, let's consider the options that lead us to here. So x is equal to 2, probability number of children is equal to 2. So we know in that case, that means that we have a boy and a girl. So that's what's happened here. So that the only way that can happen in this order is if we have probability, we have a boy first and a girl second. So you'll notice I put the "and" word in capitals there because that's obviously a very important term or feature when we're talking about probabilities. Now, as I said before, I made the imposition that the genders of the individual births are independent. So therefore, if we've got the probability of A and B occurring and they're independent events, that's just equal to the multiplication of the 2. So probability of having a boy first times by the probability of having a girl second. So we'll put in the probabilities. The probability of having a boy in the first go is 0.5. And the probability of having a girl in the second go is equal to 0.5. 0.5 multiplied 0.5 is equal to 0.25. 0.25. Now here, we could very easily find this component without having to go any further and look into any reasoning. So obviously this is essentially, let me start again. Under the rule that the sum of the probabilities has to equal 1, if I want to find out what this probability is, it's just the difference between 1 and the sum of these components. However, I will show you that we do get that out by following the logic that we're using here. So the probability x is equal to 3. So now we've got 3 children. So as I was saying before, this can happen under 2 different circumstances. That is, we either have 3 boys in a row, and that's it, we're out. So it's going to be probability 3 boys, or we have 2 boys and 1 girl. So this situation is 3 boys in a row, we stop. This is, we have 2 boys to start off with, we keep going, and then we get a girl on the 3rd try. Now, just like before when I split up the AND situation, so it was a multiplication, when the events are independent, as they are here, when we've got an OR, that goes from an OR to a plus. So that becomes equal to the probability 3 boys plus the probability of 2 boys and 1 girl. So what we'll do is we'll solve each component individually and then sub it back in for the probability x is equal to 3. Sorry about that. So probability of 3 boys is equal to the probability boy first and boy second and boy third. Now going to, assuming that each birth is independent of each other, we can split that up. So that's equal to the probability boy first times by the probability boy second times by the probability boy third. Now these each all have the same probability, so it's just 0.5 times by 0.5 times by 0.5, which is equal to 0.125. Okay, so now we've got this component, and now let's get this component here. So probability 2 boys and 1 girl is equal to probability boy first and boy second and girl third. So again, assuming that each of the births are independent of each other, we can split that up. So that's equal to, sorry about that showing up, the probability boy first times by the probability of boy second times by the probability of girl third. Subbing in those probabilities are all 0.5 times 0.5 times 0.5, which equals 0.125. So now in terms of this probability x equals 3, we found the probabilities for each of the components, so let's just add them together to find the probability x is equal to 3. So the probability x is equal to 3 then becomes 0.125, so the probability of 3 boys, plus this probability which is 2 boys and then 1 girl, 25, which is equal to 0.25, which is the difference between 1 and 0.5 added to 0.25. So now we've got our discrete probability distribution. So I'm sorry, I apologize if I've been through this before. The reason why it's a discrete probability is if we have a look at the variable x is a numerical value and it can only take on whole number representation. So we can't have 0.5 of a kid or 0.7 of a kid. So therefore, these are the only 3 values it can take. When all of the values are of the type integer or whole numbers, that means you're dealing with a discrete. And that's important because when we're answering what is the expected number of children in the family, we have to use this formula when we're working with a discrete probability distribution. So the way that we calculate this is we need to multiply x times by its corresponding probability for the different values, so that we have here. So I'm going to do that in this third column here, and then we apply the sum operator, which is this symbol here. So here we're going to have x times by the probability of x, and so this is going to be equal to 1 times by 0.5. The next one will be I should put the answer, which is equal to 0.5. The next is 2 times by 0.25, which is equal to 0.5. And then lastly we have 3 times by 0.25, which is equal to 0.75. Okay, so now we've calculated x times by the probability of x for each of the different values that x could take. We now just take the sum. So therefore we have, just go under here, effective value of x is equal to 0.5 plus 0.5 plus 0.75, which is equal to 1.75. And so therefore can expect to see 1.75 children in a randomly selected family. Okay, so that's all I'm going to answer in this question, simply because if we have a look at what is the expected number of boys in this family, all you need to do is apply the exact same type of reasoning. So have a think about the different values of boys it can take. So in comparison to x, where x is the number of children, we can actually have 0 boys. So in terms of this situation, we can have a minimum of 0 boys, a maximum of 3 boys, because remember, if we get up to 3 boys, that's it, we stop. And then just have a think about the different situations which lead us to have 0 boys, 1 boy, 2 boy, and 3 boys, and then find their corresponding probability. From that, you'll then be able to find the expected number of boys, and then the same logic applies for the expected number of girls, but this one is much simpler than part C. So anyway, I hope that was useful. If you have any questions, please comment on the Facebook page or comment here. Subscribe, like the video if you found it useful. And yeah, so I hope that was of use, and I will post up another one soon. Okay.